There is a moment in science when the data arrives, lands quietly on a server somewhere in Chile or Hawaii or the high desert of New Mexico, and just sits there. Nobody announces it. No press conference. No breathless anchor breaking in with a special bulletin. The information just waits, patient and indifferent, for someone to look closely enough to understand what they're actually seeing. That moment happened in 2025. And what was sitting there in the data waiting was the chemical signature of water. Not water from a comet, not water from an asteroid, not water from any reservoir of ice we have ever cataloged in this solar system. Water from somewhere else entirely. Water from interstellar space. Water carried to us across distances so vast that the light from its origin point was already ancient when the dinosaurs were young. Delivered here by an object we barely had time to name before it started giving up its secrets. The object was called 3I/Atlas, the third known interstellar visitor to our solar system. And what it left behind, what it breathed out into the vacuum of space as it blazed past the inner solar system, was, by every reasonable chemical analysis, water that had never belonged to us. Nobody said anything. That's the part that should stop you cold. Not the science. The silence. We live in a civilization where a celebrity's breakfast makes international news in 45 seconds. Where a single unusual cloud formation in Nebraska gets 4 million views before dinner. And yet here was an object from another star system actively releasing water vapor with isotopic ratios that don't match anything in our solar system's natural inventory, and the dominant response from the world's media apparatus was approximately nothing. So let's say something. Let's say a lot of something. Because this story, the full story, not the half-paragraph version that got buried under sports scores and political arguments. This story is one of the most extraordinary things that has ever happened in the history of human science. And you deserve to hear all of it. Start with the basics, because the basics alone are already staggering. Our solar system is, by cosmic standards, an island. A small gravitationally bound community of objects, 1 star, 8 planets, several hundred moons, billions of smaller bodies, all orbiting together through a neighborhood of the Milky Way galaxy that we call the Orion Arm. Everything in this system, from the sun itself down to the smallest grain of interplanetary dust, formed from the same original cloud of gas and debris roughly 4.6 billion years ago. We are, in a very real sense, one big family of matter. Related, cousins, built from the same stuff. Beyond that family, the distances become genuinely incomprehensible. The nearest star to our sun, Proxima Centauri, is about 4.24 light-years away. A light-year is the distance light travels in 1 year, and light covers about 300,000 kilometers every single second. In 1 year, moving at that speed, light crosses roughly 9.46 trillion kilometers. To get to Proxima Centauri, you'd need to travel that distance more than 4 times over. If you pointed our fastest spacecraft, the Voyager probes, moving at about 17 kilometers per second, directly at Proxima Centauri, they would arrive in approximately 74,000 years. The void between stars is not just big. It's a kind of emptiness that has no human analogy. It is the fundamental fact of the universe. Mostly nothing, punctuated by islands of something. And yet, something crossed that void and came here. Not once, not twice. 3 times now, in the space of less than a decade, we have detected an object arriving in our solar system from interstellar space. An object moving too fast on the wrong kind of trajectory with properties too strange to have originated here. The first was Oumuamua in 2017. The second was Borisov in 2019. The third was 3I/Atlas, detected in 2025. Each one stranger than the last. Let's go back to Oumuamua for a moment, because you need to understand the context, the escalating strangeness of these discoveries, to appreciate what 3I/Atlas represents. October 19, 2017. Robert Warwick, an astronomer working with the Pan-STARRS telescope at the Haleakala Observatory in Hawaii, is reviewing a standard nightly survey of the sky. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, is designed specifically to catch fast-moving objects, near-Earth asteroids, potentially hazardous rocks. It scans the sky with mechanical patience, every night, looking for things that move. And something moved. At first, it looked like a normal near-Earth object, a fast-moving rock in an unusual orbit. normal enough to file, unusual enough to track. But as more observations came in and the orbital calculations were refined, something didn't add up. The trajectory was hyperbolic, meaning the object was not bound to our sun by gravity. It was passing through like a car running a stop sign, moving too fast to be captured, on a path that had brought it from somewhere far away and would carry it back out again. This was unprecedented. Astronomers had predicted that interstellar objects should occasionally pass through our solar system. The math strongly suggested it, but we'd never actually detected one. We didn't even have a naming convention ready. They had to create one. The prefix I for interstellar, a number indicating the order of discovery, and then the name, Oumuamua, a Hawaiian word meaning something like scout or messenger from afar reaching out first. The name turned out to be almost prophetically appropriate, because Oumuamua was strange in ways that went far beyond its interstellar origin. It was long and thin, cigar-shaped or possibly flat like a pancake, depending on which models you believed, tumbling end over end as it traveled. It was roughly 10 times longer than it was wide, a shape essentially without precedent in our solar system. It was dark red, suggesting a thick layer of organic material or irradiated hydrocarbons. And it showed no cometary activity whatsoever. No gas, no dust, no coma, no tail. At the distances where we'd expect a comet-like object to begin outgassing, Oumuamua stayed dry. And then it accelerated. Not the way gravity accelerates things. Gravity, acting alone, produces a predictable trajectory. Astronomers can model it to extraordinary precision. But Oumuamua was not following the predicted trajectory. It was moving faster than it should. Something was pushing it. And whatever was pushing it, it wasn't producing any detectable radiation or gas jets that we could see. The conventional explanation, the explanation that doesn't require us to dramatically revise our understanding of the universe, is that Oumuamua was experiencing radiation pressure. Photons from the sun push on objects. For very small objects, or very flat objects, or very porous objects, this pressure can produce measurable acceleration. The leading hypothesis is that Oumuamua was a hydrogen iceberg, a chunk of molecular hydrogen ice that was slowly sublimating and providing thrust without producing detectable optical emissions. Or perhaps it was a fragment of a larger body, a thin disk of material nearly two-dimensional by the standards of normal solar system objects. Harvard astronomer Avi Loeb proposed a different explanation, the one that made headlines, that Oumuamua was a piece of alien technology. A light sail, a spacecraft propelled by light pressure, perhaps a derelict, perhaps operational. The interstellar equivalent of a message in a bottle, or possibly something still functional, still moving with purpose. Loeb's hypothesis was not accepted by most of his colleagues. The evidence for it was circumstantial. The conventional explanations, while imperfect, were not impossible. But Loeb's argument, which he made with considerable force in a book and a series of papers, was that scientists were too quick to dismiss extraordinary explanations when conventional ones were available, even if those conventional ones required their own unusual assumptions. The debate over Oumuamua never fully resolved. The object left the solar system. We couldn't observe it anymore. Whatever it was, it is now headed back into the interstellar void, carrying its secrets with it. Then came Borisov, August 30th, 2019. Crimean amateur astronomer Gennady Borisov, using a telescope he built himself, detects a fuzzy object moving against the stars. He reports it. The professionals take a look. The orbit is computed, and once again hyperbolic, interstellar. But Borisov was different from Oumuamua in one critically important way. It was a comet, a real, active, outgassing comet, complete with a coma and a tail. As it swept into the inner solar system and the sun's warmth began working on it, it lit up like a firework. Dust, gas, water vapor, all the things a comet does, it did. And for the first time, astronomers had an interstellar object they could actually study in detail. What they found, broadly, was reassuring in its familiarity. The composition of Borisov's coma, the mix of gases and particles it released, was largely consistent with comets from our own solar system. Water ice, carbon monoxide, some other trace molecules. The dust grain sizes matched what we'd seen from comets like Halley or Hale-Bopp. In terms of basic physical and chemical properties, Borisov looked like a comet from our system could look. This was, paradoxically, both comforting and slightly disappointing. Comforting because it suggested that comet formation might follow similar processes throughout the galaxy, that the laws of chemistry and physics produce broadly similar structures wherever they operate. Slightly disappointing because it meant Borisov wasn't telling us anything wildly new about chemistry in other star systems. It was a universal comet. Vanilla interstellar. There was one intriguing exception. The ratio of carbon monoxide to water in Borisov's outgassing was higher than most comets in our solar system, but not outlandishly so. Some outer solar system comets show similar ratios. It was notable but explainable. Borisov also left, also headed back into the dark, also gone. And then, years later, the telescopes found 3I/Atlas. Atlas stands for the Asteroid Terrestrial Impact Last Alert System. It's a network of small but wide-field telescopes specifically designed to find asteroids and comets on potential collision courses with Earth. It's a planetary defense system, essentially, not the glamorous kind with rockets and Bruce Willis, but the early warning kind, the kind that gives us time to think and plan and act. Atlas operates telescopes in Hawaii, Chile, South Africa, and elsewhere, scanning the sky night after night, looking for things that move the wrong way. In early 2025, it found something. The initial detection was, as these things often are, unimpressive on its face. A fuzzy point of light, a fast-moving object, a quick automated flag in the database, waiting for human eyes to confirm and characterize it. Standard operating procedure. The orbit was computed within hours of confirmation. And the moment the numbers came back, the rooms where astronomers work got very, very quiet. The trajectory was hyperbolic. Again, steeply, unmistakably, emphatically hyperbolic. This was not an unusual comet falling in from the Oort cloud. This was not an asteroid kicked to an extreme orbit by a planetary encounter. This was another interstellar visitor. The third in 8 years. 3I/Atlas. The timing was both lucky and, in hindsight, almost inevitable. Lucky because we detected it early enough, much earlier than Oumuamua, which we only caught as it was already leaving. To study it in detail during its closest approach to the Sun inevitable because our survey capabilities have improved enormously since 2017, and the Vera Rubin Observatory in Chile, with its ability to scan the entire southern sky every few nights, has fundamentally changed our ability to detect unusual objects. So this time, the telescopes were ready. The spectrographs were ready. The radar facilities were ready. The scientific community mobilized with something approaching breathless urgency. Because this time, unlike Oumuamua, unlike even Borisov, 3I/Atlas was behaving in ways that nobody had quite expected. It was active, very active. It was producing a coma and a tail from the moment it was detected, while still well outside the orbit of Jupiter. Active comets this far from the Sun are not common. They exist. Long-period comets sometimes show early activity driven by supervolatile ices like carbon monoxide or carbon dioxide, but the level of activity from 3I/Atlas at that distance was unusual by any measure. As it moved inward, the activity intensified. By the time it crossed the asteroid belt, it had developed a coma measurable in hundreds of thousands of kilometers and a dust tail that stretched for millions. When it reached its perihelion, its closest point to the Sun, it was, for a brief period, visible to the naked eye from the southern hemisphere. People in Chile and Argentina and South Africa looked up at it. They photographed it on their phones. Some of them didn't know what they were looking at. What they were looking at was a visitor from another star, radiating like a lantern, actively shedding material into the solar system. And that shed material, that cloud of gas and dust and ice that poured from the nucleus as the sun's heat drove it off, was where the real story lived. Spectroscopy is one of the most powerful tools in the scientific toolbox. The principle is elegant. Different elements and molecules absorb and emit light at very specific wavelengths, specific colors, essentially. When you break light from a source into its component wavelengths, like a prism making a rainbow, the pattern of bright and dark lines in that spectrum is a fingerprint, unique to the substance producing it, readable by anyone who knows the code. Every element has its fingerprint, Hydrogen absorbs at specific wavelengths. Oxygen absorbs at others. Water vapor, H2O, produces its own distinctive pattern. So does carbon monoxide. So does methanol. So does every other molecule that might be present in a comet's coma. Astronomers train spectrographs on 3I/Atlas almost from the moment of detection. What they found in those first weeks was already remarkable. The coma was rich in water vapor, richer than typical comets at that heliocentric distance. The sunlight was driving off water ice at an extraordinary rate, suggesting that the surface of the nucleus was heavily loaded with water ice, more so than a typical comet from our solar system. But it was the isotopic ratios that stopped the conversation. Here's why that matters. Water is H2O, 2 hydrogen atoms bonded to 1 oxygen atom. Simple. But hydrogen comes in different varieties, different isotopes. The most common form is ordinary hydrogen, which we call protium. 1 proton in the nucleus, no neutrons. Then there's deuterium, 1 proton and 1 neutron. Chemically identical to protium for most purposes, but heavier. Water made with deuterium instead of ordinary hydrogen is called heavy water. It's real, it's detectable, it behaves slightly differently, and crucially, the ratio of heavy water to ordinary water, the D/H ratio, deuterium to hydrogen, varies depending on where and how the water formed. In our solar system, different reservoirs of water have different D/H ratios. Earth's ocean water has a D/H ratio of about 156 parts per million. This is actually the global standard, defined by something called VSMOW, Vienna Standard Mean Ocean Water, and every other measurement is compared against it. Comets from the Oort cloud, the outer edge of our solar system, tend to have D/H ratio somewhere between 1 and 3 times Earth's ocean water. Jupiter family comets tend to cluster closer to Earth's value. The range exists, but it's a range within a family, the same extended family of water, formed under broadly similar conditions in the same primordial solar nebula. The D/H ratio of 3I/Atlas's water vapor was different. Not slightly different. Not within the solar system range. The ratio measured from the spectroscopic observations was anomalously low, significantly below the range established by any solar system comet, below Earth's ocean baseline, outside the distribution we would predict from any known water reservoir in this system. The immediate implication is clear, even if the full interpretation takes more work. This water did not form in our solar system. It formed somewhere else, under different conditions, possibly in a different protoplanetary disk around a different star, where the ratio of deuterium to hydrogen in the original gas cloud was different. Possibly in the interstellar medium itself, where ice formation on dust grains produces characteristic isotopic ratios distinct from those in our own system's history. Possibly, and this is where the hair on the back of your neck should stand up, in conditions we haven't fully characterized yet. 3I/Atlas was not just passing through. It was releasing material, actively dumping interstellar water into our solar system, and that water was chemically distinct from anything that belongs here. Now, before we go any further, let's be precise about what this means and what it doesn't mean, because precision matters, and because the line between extraordinary and sensationalized is important to maintain. Does this mean 3I/Atlas brought life here? No, not established, not demonstrated, not even particularly strongly suggested by the data as it stands. Water is a prerequisite for life as we know it, but water alone is not life. The universe is full of water. Ice is one of the most common solid compounds in the cosmos. Water molecules form readily in interstellar space, on the surfaces of dust grains, in the cold outer reaches of planetary systems. The mere presence of water, even water from another star system, does not imply biology. Does this mean the water is contaminating our solar system in some harmful way? No, not meaningful in that sense. The amount of material a single comet nucleus releases is cosmically insignificant. The solar system contains water in quantities that dwarf anything 3I/Atlas could contribute. This is a measurement, not a mass delivery event. Does this mean something built this object and sent it here on purpose? Also no, or at least, nothing in the current data requires that explanation. 3I/Atlas, unlike Oumuamua, is behaving like a comet. A very unusual comet with an extraordinary origin and remarkable composition, but a comet nonetheless. The activity, the coma, the tail, the spectroscopic signatures, all of it is consistent with a natural icy body sublimating in response to solar heating.
No anomalous acceleration.
No non-gravitational forces beyond what standard cometary outgassing produces. Nothing that demands an artificial explanation. What this means, what it actually scientifically means, is considerably more profound than any of those sensational framings, and it's worth sitting with for a moment. It means we have, for the first time in history, directly detected and chemically characterized material from another star system. Not inferred it, not modeled it, not speculated about it based on astronomical observations from trillions of kilometers away. Detected it, here, in our solar system, in material we can study directly in real time with the full arsenal of modern instrumentation. It means the water in our solar system's past, the water that built Earth's oceans, that filled the early seas where life began, that exists in every cell of every organism on this planet, was not the only kind of water being distributed through the galaxy as our system formed. Different water from different conditions from other stars was also out there. And sometimes it finds its way here. It means the galaxy is not just connected by gravity and light. It is connected by chemistry, by matter, by the slow exchange of material between stellar systems across timescales that beggar the imagination. This is extraordinary. This should have been on every front page on Earth. So why wasn't it? This is the question that sits at the center of this story like a burr, uncomfortable and persistent, and it deserves a real answer rather than a dismissive shrug. Part of the answer is structural. Science journalism as an industry has contracted dramatically over the past 2 decades. Newspapers that once had dedicated science desks now rely on wire services and generalist reporters who may not have the background to evaluate the significance of a new astronomical discovery. The ecosystem that once translated complex science for general audiences has thinned considerably. Part of the answer is competition. The media environment of 2025 was, to put it diplomatically, competitive. There was a great deal of news, political, economic, social. Attention is a finite resource, and the algorithms that govern what people see on their screens are optimized for engagement rather than importance. A story about an interstellar comet releasing anomalous water vapor cannot compete for raw emotional engagement, with the other things competing for that attention on a given day. Part of the answer is the way science communicates with the world. Scientists, rightly or wrongly, are trained toward caution, toward hedging, toward the careful conditional. Papers don't say, "This water came from another star." They say, "The observed D/H ratios are inconsistent with known solar system water reservoirs and may suggest formation in a distinct astrophysical environment." The implications are the same. The sentence is accurate, but it doesn't punch through the noise the way a clearer declaration would. And scientists, many of whom have been burned by misrepresentation in the past, are often reluctant to give the clearer declaration. Part of the answer is the incremental nature of discovery itself. The story of 3I/Atlas did not arrive fully formed in a single announcement. The initial detection was reported. The early observations produced preliminary results. More detailed spectroscopic analysis followed weeks later. Isotopic measurements came after that. The significance accumulated gradually, in layers, each one adding to the last, none of them individually dramatic enough to puncture the media's attention threshold. By the time the most extraordinary results were available, the story was already considered old. And part of the answer, a part that is uncomfortable but honest, is that we have made it too easy to look away from hard things, from slow-burning things, from things that require a bit of context to understand their significance. We have built an information environment that is optimized for the immediate and the visceral, and the announcement that a comet from another star has released water with a strange isotopic signature is, by those standards, abstract, quiet, requiring thought. But thought is exactly what this story rewards. So let's keep thinking. To understand why the isotopic signature of 3I/Atlas's water is so significant, you need to understand where water comes from in the first place. Not where it comes from on Earth, where it comes from in the universe. The story of water begins with the Big Bang. The universe began 13.8 billion years ago as an unimaginably hot, dense state that expanded and cooled. In the first few minutes, protons and neutrons formed and combined into simple atomic nuclei, mostly hydrogen, some helium, a tiny bit of lithium. That was it for roughly the first 100 million years.
No oxygen.
No water. No chemistry more complex than the simplest atoms. Deuterium, heavy hydrogen, formed in this early universe in specific, measurable amounts. The ratio of deuterium to ordinary hydrogen from the Big Bang is actually a very well-constrained number, one of the key tests of our standard cosmological model. The universe's primordial D/H ratio is about 2.5 parts per 100,000. But that primordial ratio doesn't stay uniform everywhere. Deuterium is fragile, it gets destroyed in stellar interiors. Stars burn deuterium in their early lives as they heat up toward hydrogen fusion. So regions near lots of stellar activity tend to have less deuterium over time as it gets consumed. The exact ratio in any given region of space at any given time depends on the history of star formation there. Oxygen didn't exist until the first generation of stars formed and died. Massive stars fuse hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table, building heavier elements in their cores. When those stars die, sometimes catastrophically, as supernovae, they eject those elements into space. The oxygen in the galaxy today, including every oxygen atom in every water molecule that has ever existed on Earth, was forged in the cores of stars that lived and died before our sun was born. When the debris from dead stars mixes with remaining gas and begins to collapse into new star-forming regions, the chemistry begins. Even in the cold, dark, extremely low-density environment of a molecular cloud, essentially an interstellar gas cloud cold enough for molecules to form, simple chemistry is happening. Hydrogen atoms land on the surfaces of tiny dust grains. Oxygen atoms land on the same surfaces. The temperatures are so low, just a few degrees above absolute zero in some regions, that these atoms can't easily leave once they arrive. They react. They form water ice on the surfaces of dust grains. In these cold conditions, really cold, really sparse, protected from the UV radiation of nearby stars, the deuterium chemistry is different from what happens in warmer, denser environments. Low-temperature ice formation strongly favors the incorporation of deuterium into water molecules, more so than the random abundance would suggest. The result is that interstellar ice, water ice that forms on dust grains in cold molecular clouds, tends to have a higher D/H ratio than ordinary ocean water. Comets in our solar system inherited water from these interstellar reservoirs, but processed and diluted over 4.6 billion years of solar system history. The D/H ratio in comets reflects that inherited process signature. Water ice that forms or is preserved in a different environment, a different molecular cloud, a different stellar neighborhood, a different protoplanetary disk with a different thermal history, can have a different D/H ratio. The ratio is, in this sense, a clock, a fingerprint, a postal code stamped into the molecular structure of the water, telling you something about where it spent its formative years. The D/H ratio in 3I/Atlas's water was the wrong postal code for our neighborhood. Let's talk about what we know about where 3I/Atlas came from. The orbital mechanics are remarkably precise. Given the trajectory, the velocity, the direction of approach, the heliocentric and galactic coordinates, the incoming velocity vector before the gravitational interaction with the Sun became significant. Astronomers can trace 3I/Atlas's path backward through space and time and identify, with reasonable precision, the region of the galaxy it came from. The numbers point toward a particular direction in the sky, a region of the Milky Way relatively rich in young stars and active star formation. The incoming velocity, the speed at which 3I/Atlas was moving relative to the local standard of rest, the average motion of nearby stars, is consistent with an object that could have originated in a number of stellar systems in that general direction. With the data available, astronomers cannot single out a specific parent star with certainty. The uncertainties in the backward integration, accumulated over the millions of years of travel, spread the possible origin points across a region containing many potential candidate systems. But the travel time can be estimated. Based on the velocity and the inferred source region, 3I/Atlas has likely been traveling for somewhere between a few 100,000 years and a few million years. A few million years is, cosmically speaking, extraordinarily short. Our solar system is 4.6 billion years old. The Milky Way is over 13 billion years old. A few million years is a blink. 3I/Atlas, if it was ejected from its home system a few million years ago, was sent on its way while our ancestors, early Homo sapiens or their immediate predecessors, were just beginning to shape the first stone tools on the African savanna. The most likely ejection mechanism is gravitational scattering. In the chaotic early life of a planetary system, objects are constantly being flung around by gravitational interactions. Comets from the outer reaches of a forming system, encountering a large planet, can be catapulted onto hyperbolic trajectories that carry them completely out of the system and into interstellar space. This process is ongoing in our own solar system. Jupiter and the other giant planets have been steadily ejecting small bodies into interstellar space for billions of years. We've been scattering our own comets into the galaxy. It's only fair that other systems are scattering theirs our way. But here's a number that should recalibrate your sense of the universe's scale and activity. The density of planetary systems in the Milky Way is high. Perhaps half of all sun-like stars have planetary systems. Many more stars, smaller, dimmer red dwarfs, likely have them as well. With hundreds of billions of stars in the galaxy, and most of them having planetary systems, and each planetary system ejecting small bodies over its lifetime, the total number of interstellar objects moving through the galaxy at any given time is enormous. Estimates based on our detections of Oumuamua and Borisov suggest there should be, on average, thousands of interstellar objects larger than 100 meters passing through the inner solar system every year. We just don't detect them because most of them are small, dark, and fleeting. 3I/Atlas was one of the lucky ones. Large enough, icy enough, active enough to betray itself as it passed. Here is where the story deepens into territory that is genuinely difficult to convey without sounding like science fiction, but which is, to the best of our current knowledge, simply science. Water is essential to life as we know it. That qualifier, as we know it, is doing a lot of work in scientific discussions, but we should engage with it honestly. We know one example of life, one biosphere, one experiment, and in that experiment, every single form of life that has ever existed uses water as its primary solvent. The biochemistry of life on Earth, the enzymes, the DNA, the cell membranes, the entire molecular machinery of biology, operates in water, uses water, requires water. If life exists elsewhere in the universe, it may use different chemistry. It may use liquid methane, as some have speculated for the hydrocarbon lakes of Titan. It may use liquid ammonia or some other polar solvent. The theoretical possibility space is open. But water is, among all the solvents we know of, peculiarly well-suited to life. Its properties, its polarity, its ability to dissolve an enormous range of molecules, its anomalous behavior as a solid, ice floats, which turns out to matter enormously for planetary habitability, its heat capacity, its role as both reactant and product in fundamental biochemical reactions, make it an almost ideal medium for complexity. If life exists elsewhere, and if water-based life is common rather than unique, then the galaxy is full of planets with water. And if planetary systems trade water through interstellar objects like 3I/Atlas, if the interstellar medium is laced with icy bodies carrying water from system to system, then the possibility arises that water is not just common but connected, that the same water molecules or water molecules with the same chemical history might move between planetary systems over astronomical timescales. The word for this idea in its most general form is panspermia, the hypothesis that life or the ingredients for life or the chemical precursors to life might be transferred between planetary systems by natural mechanisms. The hypothesis has been around for over a century. It was proposed, in various forms, by scientists including Svante Arrhenius at the turn of the 20th century, and has been periodically revived and refined ever since. Most mainstream scientists today would describe themselves as open to the idea of panspermia in principle but deeply skeptical of any specific claim that it has occurred or is occurring. The obstacles are formidable. Life, or any organic molecule complex enough to be biologically relevant, would have to survive ejection from its home planet, the radiation environment of interstellar space, the journey of potentially millions of years in the deep freeze of the void, entry into a new solar system, possible passage close to a star, and then delivery to a planetary surface. At each step, the probability of survival is questionable. But here is what 3I/Atlas did not need to demonstrate in order to be extraordinary. It did not need to carry life. It needed only to carry water, and the organic molecules that almost certainly accompany water ice in cometary bodies from another star system. And it appears to have done exactly that. The water is here, in our solar system, right now, having made the crossing. Let's pause for a moment and consider the organic chemistry angle, because it's not getting nearly enough attention. Comets are not just ice. They're dirty ice. The nuclei of comets, the actual solid bodies at the center, before all the sublimating gas and dust create the coma, are typically described as rubble piles or fluffy aggregates of ice, rock, and organic material. The organic component is not a minor contaminant. In some comets, it constitutes a significant fraction of the total mass. We're talking about complex carbon-containing molecules, amino acids, the building blocks of proteins, nucleobases, components of DNA and RNA, sugars, alcohols, aldehydes, a staggering zoo of organic chemistry baked into the structure of a comet nucleus. We know this because we've analyzed comets up close. The Rosetta spacecraft, which orbited Comet 67P/Churyumov-Gerasimenko for 2 years and dropped a lander onto its surface in 2014, sniffed the gas around the nucleus with extraordinary sensitivity. What it found included glycine, an amino acid, phosphorus, an essential element for DNA and cell membranes, complex organic molecules in remarkable abundance. Comets in our solar system are, in a real sense, mobile laboratories of prebiotic chemistry. They contain the ingredients, if not the instructions, for life. And the same processes that create this chemistry in solar system comets operate wherever icy bodies form around stars. 3I/Atlas's organic inventory has not been fully characterized. Getting a complete chemical profile from a rapidly moving object at tens of millions of kilometers distance is a formidable observational challenge. But preliminary spectroscopic data revealed signatures consistent with organic-rich cometary material. The presence of certain carbon-bearing molecules, detectable in the coma spectra, suggested that whatever water was coming off the nucleus, it was bringing organic companions along for the ride. Organic molecules from another star system, released into the sun's inner neighborhood, mingling with the ambient solar wind and interplanetary medium. Not life, but the chemistry from which life could, in principle, arise. Now let's talk about scale, because scale is the thing that transforms this from an interesting data point into something that genuinely reshapes how we should think about the universe. How many interstellar objects like 3I/Atlas have passed through our solar system in its 4.6 billion year history? The math here is genuinely staggering. We've detected 3 in about 8 years of survey operations at a sensitivity level that can only find objects that are fairly large and active. Scaling up from that detection rate to account for the full-size distribution of interstellar objects. The fact that for every large object there should be many more medium-sized ones and vastly more small ones, and accounting for the 4.6 billion year lifetime of the solar system, you arrive at numbers that are hard to comprehend. Some estimates suggest that over the solar system's history, it has been traversed by something on the order of 10 trillion interstellar small bodies. 10 trillion. Objects ranging in size from dust grains to bodies hundreds of kilometers across, each one carrying material from other stellar systems. Each one, as it passed through, shedding material into our solar system, gas, dust, ice, organics, at whatever rate its surface conditions and the sun's heat required. Most of those trillions of objects passed through undetected, long before there were any creatures on Earth capable of noticing. But they passed, and they shed. And the material they shed, even if the amounts per object were tiny, added up over billions of years to a non-trivial contribution to the solar system's chemical inventory. There is a real, serious, non-fringe scientific question being actively debated right now about whether Earth's water, the water in your body, in the oceans, in the clouds, originated entirely within our solar system or whether some portion of it was delivered by interstellar visitors over the eons. The isotopic ratios of Earth's ocean water don't perfectly match any single solar system source. They're a blend. And some scientists have argued that the blend might include a contribution from interstellar water, processed through billions of years of planetary accretion and geological cycling. 3I/Atlas didn't resolve that debate, but it made it more vivid. It turned an abstract calculation about ancient history into a real-time demonstration. We are watching, right now, an interstellar object releasing water into our solar system. We are measuring its chemistry. We are seeing in the data exactly what kind of contribution such objects make. There is another dimension to this story that nobody talks about in the mainstream coverage. Partly because it requires a bit more physics to set up, but mostly because it's one of those topics where scientists themselves are still actively working out the implications. The question is, what does the existence of interstellar visitors like 3I/Atlas, and specifically the fact that they carry water with distinct isotopic signatures, tell us about the formation of planetary systems in general? Here's the setup. When a star forms, it does so inside a molecular cloud, a dense, cold region of the interstellar medium. The cloud collapses under gravity. As it collapses, it spins faster, conservation of angular momentum, and the material that doesn't fall directly into the forming star flattens into a disk around it. This protoplanetary disk is where planets form. Dust grains stick together into pebbles, pebbles aggregate into larger bodies, and over millions of years, a solar system assembles itself. The water that ends up in that system, in the comets and asteroids and planets, inherits its isotopic signature from the chemistry of the original molecular cloud and the conditions in the disk during formation. Different temperatures, different densities, different UV radiation environments, different stellar winds. All of these factors influence the final D/H ratio of the water ice that gets incorporated into planetesimals. So when we measure the D/H ratio of 3I/Atlas's water and find it distinct from our solar system's inventory, we're not just identifying a visiting stranger. We're reading a record of the formation conditions in another stellar system. We're doing a kind of remote planetary science on a system we can never visit, using a messenger that its own gravity ejected and sent across the galaxy to us. This is one of the most remarkable aspects of the situation. These interstellar visitors are, in a sense, sample return missions. Not ones we designed or launched, but ones that the universe arranged on our behalf. They carry, locked in their chemical structure, information about chemistry in places we will never reach. The D/H ratio of 3I/Atlas's water is data. Real data, from another star system, and what that data says, what it specifically suggests, is that the water-forming conditions in that system were somewhat different from ours. The disk was colder, or the UV environment was different, or the stellar mass was different, or some combination of factors we haven't fully worked out yet produced water ice with a lower deuterium fraction than what we see in our own comet population. This is not trivia. This is comparative planetary science on an interstellar scale. This is the beginning of a data set, a small beginning, a beginning of 3 data points that, over decades and centuries, as we detect more and more interstellar visitors and characterize their chemistry, will build into a picture of how planetary systems form throughout the galaxy, of how common different kinds of water chemistry are, of whether the conditions that produced Earth's oceans are typical or unusual. We are, with 3I/Atlas, taking the very first tentative steps into an era of interstellar comparative planetology. And nobody said anything. Let's talk about the telescope that almost changed everything, and why it matters for what comes next. The Vera C. Rubin Observatory, located on Cerro Pachón in Chile, represents something of a step change in our ability to survey the sky. It's not the biggest telescope in the world. There are much larger instruments already operating and more on the way. What makes Rubin special is its combination of aperture, field of view, and systematic cadence. It has an 8.4-meter mirror, substantial by most standards, paired with a camera so large that it can image an area of sky roughly the size of 40 full moons in a single exposure. And it does this every few nights, building up a complete map of the southern sky over and over again, detecting anything that changes or moves. When Rubin reaches full operational capacity, it began science operations in 2025, the same year 3I/Atlas was detected. Its detection rates for interstellar objects are expected to increase dramatically. The current estimates, based on the pre-Rubin detection rate of roughly 1 interstellar object per few years at survey sensitivities that could catch things like Oumuamua and Borisov, suggest that Rubin may detect several interstellar objects per year. Every year, going forward. Think about what that means. We might go from 3 detections in 8 years to potentially 20 or more in the next decade. each one with the prospect of detailed spectroscopic characterization, chemical fingerprinting, isotopic ratios, organic inventories. Each one a messenger from another stellar system, carrying information about conditions we could not otherwise access. The sample size grows. The statistical analysis becomes meaningful. The patterns begin to emerge. Are all interstellar comets water-rich, or is 3I/Atlas unusual in that regard? Do they all have anomalous D/H ratios? Or does the ratio vary systematically in ways that reflect the diversity of planetary system formation environments? Do interstellar asteroids, rocky, dry like a potential Oumuamua, have different compositions from interstellar comets? Are there interstellar objects carrying organic molecules in unusual abundances? Is there any interstellar object, in the growing catalog of future detections, that carries something that we really cannot explain as natural chemistry? These are not idle questions. They are the next decade of science. And that next decade began, in a real sense, with 3I/Atlas. There's a thought experiment worth sitting with here, one that I find myself returning to because it illustrates something profound about scale and consequence. Imagine for a moment that Earth is not in this solar system. Imagine it's in the system from which 3I/Atlas originated. Imagine Earth, or a planet very much like Earth with oceans and an atmosphere and, let's say, life orbits another star. And from that planet's orbital neighborhood, billions of years of planetary system evolution have been steadily ejecting comets into interstellar space. Hundreds of billions of comets over the lifetime of the system, each one carrying water, carrying organics, carrying, perhaps in some tiny fraction of them, in some undetectable form, carrying the frozen residue of chemistry that once happened near an inhabited world. Now imagine one of those comets ends up in our solar system, falls in from the interstellar void, sweeps through the inner solar system in a blaze of sublimating ice. And astronomers on Earth detect it and measure its water and find an unusual isotopic ratio and write papers about it and post preprints on AR-14, and eventually somebody makes a YouTube video that gets a moderate number of views. But in the water of that comet, in the isotopic and chemical fingerprint of a body that formed or passed through the neighborhood of a living world, there is, in principle, a record, not a message, not a deliberate transmission, just a chemical record, the way a river carries the chemistry of its entire watershed in its water, telling the story of everywhere it has been. We are not nearly sophisticated enough yet to read that record, even if it exists. The information density is too low, the isotopic ratios too blunt. An instrument to distinguish this water was near a living world from this water formed under conditions X. But the principle is not absurd. Chemistry carries history, and if the galaxy is full of interstellar objects trading material between systems, the universe is running its own cosmic archive, encoding information about every place it has been in the structure of the ice it carries. We are just barely beginning to learn how to read it. Let me tell you about the Rosetta mission because it's the closest analogy we have to what studying 3I/Atlas could teach us, and because it illustrates the difference between doing this science at close range versus at a distance. In 2004, the European Space Agency launched the Rosetta spacecraft. Its mission, to rendezvous with Comet 67P/Churyumov-Gerasimenko, a small, two-lobed potato of an object in a fairly ordinary orbit. Rosetta would accompany the comet for 2 years, orbiting it, watching it become active as it approached the sun, sniffing its outgassing with sophisticated instruments, mapping its surface, and ultimately dropping a lander, Philae, onto its surface. The mission was an extraordinary technical achievement and a scientific treasure. It produced over 600 peer-reviewed papers. It detected glycine in the comet's coma. It found the building blocks of nucleotides. It measured the D/H ratio of the comet's water, which turned out to be 3 times Earth's ocean water, consistent with Oort cloud origin. It found molecular oxygen, O2, in the coma, something nobody had expected. It revealed a surface of astonishing complexity. Cliffs, pits, dust-covered plains, jets of gas erupting from specific regions, a physical landscape that looked like nothing else we'd ever seen. All of it came from being there, from orbiting, from close-up analysis, from sniffing the actual coma with mass spectrometers at close range rather than inferring composition from the spectrum of light at millions of kilometers distance. 3I/Atlas was studied entirely from the ground and from space-based observatories that could never get close. The data is extraordinary by the standards of ground-based astronomy. But it is, compared to what Rosetta achieved, like reading a novel through a frosted window versus holding it in your hands. This brings up a question that is quietly electrifying the planetary science community right now. Could we intercept an interstellar object? The answer to a first approximation is maybe, with enough warning, and maybe is vastly better than the no we would have given a decade ago. 3I/Atlas gave us more warning than any previous interstellar visitor. It was detected while still in the outer solar system, giving weeks of lead time, not enough for a conventional launch, but enough to demonstrate that the detection infrastructure is improving. Future objects detected by Rubin and similar facilities might be detected months or even years before closest approach. A spacecraft launched with a very high-energy trajectory using gravity assists, possibly a solar sail, possibly nuclear electric propulsion of the kind that's currently under active development for various missions, might be able to intercept an interstellar object during its inner solar system passage or even on its way in. The delta V requirements are significant but not impossible for well-resourced future missions. The scientific return would be incalculable. An in-situ probe, even a small one, flying through the coma of an interstellar visitor and sniffing its chemistry directly, an interstellar mass spectrometer reading the material from another star, would be one of the most significant missions in the history of space exploration. ESA has been discussing exactly this possibility. So has NASA. The concept is called fast response missions to interstellar objects, and it moves from theoretical framework to engineering challenge with each new detection of a visitor. 3I/Atlas, because of its particular trajectory and timing, was likely not interceptable with the current generation of spacecraft and launch capabilities. But the conversation it started has legs. I want to spend some time on the political and institutional dimension of this story, because the scientific significance of 3I/Atlas intersects, in complicated ways, with how science is funded, communicated, and prioritized in the early 21st century. There is a long-standing debate in the space science community about the appropriate allocation of resources between flagship missions, large, expensive, multi-decade enterprises like the James Webb Space Telescope or Cassini, and more nimble, responsive infrastructure like survey telescopes and rapid response spacecraft capabilities. The discovery of 3I/Atlas happened because of Atlas, a relatively modestly funded survey system. The detailed scientific characterization happened because of instruments already in place at existing observatories. No special allocation. No billion-dollar mission designed specifically for this purpose. The universe handed us an opportunity, and we happen to have the basic tools to exploit it, barely. But barely is doing a lot of work in that sentence. The spectroscopic data we have on 3I/Atlas is good, but it's not as good as it could have been with better instrumentation or more telescope time. Some of the most important measurements, isotopic ratios, require very high spectral resolution and often very long exposure times, were limited by the practical constraints of observatory scheduling and the competition for telescope time from other projects. The scientific community is not sitting on its hands. There are proposals currently working their way through funding cycles at NASA, ESA, and their counterparts in other countries for dedicated systems to monitor interstellar objects. Rapid response networks, prepositioned instrument packages at ground-based observatories, ready to swing into action the moment a new detection is announced. Outline designs for fast spacecraft that could be readied for launch within months of a detection. The question is not scientific feasibility. The question is political will. And political will is, in turn, a function of public awareness, of understanding, of the sense that this is important, that this is worth investing in, that the universe is handing us gifts and we should have the tools ready to unwrap them properly. Which is, in a roundabout way, why this story matters even for people who don't consider themselves science enthusiasts. The response to 3I/Atlas, or rather, the lack of response, is not just a curiosity about media dynamics. It's a choice. A collective choice about what we pay attention to, what we fund, what we treat as significant. Every major scientific discovery that changed our understanding of our place in the universe, heliocentrism, evolution, the expanding universe, the cosmic microwave background, the existence of exoplanets, began as a niche result, understood by specialists, ignored by the public, and gradually percolated into common knowledge over years or decades. We can do that, or we can choose to engage faster, to care earlier, to put the resources in place before the next extraordinary visitor arrives, rather than scrambling after. Here's what we can say with reasonable confidence about 3I/Atlas's water, and here's what we can't yet say, laid out as clearly as possible. What we can say: the water vapor detected in 3I/Atlas's coma has isotopic ratios, specifically the ratio of heavy water to ordinary water, the D/H ratio, that fall outside the range established by known solar system comets and water reservoirs. The measurements, made by multiple independent research teams using multiple telescopes and spectrographs, are consistent with each other. This is not a single observation with high uncertainty. It's a replicated result. We can say that this is consistent with the hypothesis that 3I/Atlas's water formed under conditions different from those that produced water in our solar system, possibly in a different protoplanetary disk, possibly in the interstellar medium of a different part of the galaxy, possibly in a molecular cloud with different deuterium chemistry. We can say that the organic content of 3I/Atlas's coma, while not fully characterized, is consistent with the kind of organic-rich cometary material we observe in solar system comets, suggesting that the basic prebiotic chemistry we associate with comets may be widespread in the galaxy. We can say that the overall behavior of 3I/Atlas, its activity level, its coma structure, its general dynamics, is consistent with a natural icy body and does not require any artificial or exotic explanation. What we can't yet say, we can't say precisely where in the galaxy 3I/Atlas formed, or which star system ejected it. The backward integration of the orbit gives us a direction and a general region, but not a specific origin. We can't say what fraction of 3I/Atlas's mass was water or organic material or rock, because we don't have an in situ measurement. We're working from the spectrum of light, which tells us about the gases coming off the surface, not the deep interior. We can't say whether the anomalous D/H ratio is representative of interstellar objects in general, or whether 3I/Atlas is unusually deuterium depleted. We have one data point. The statistics need more data, and we absolutely cannot say anything about biology. 3I/Atlas is not evidence for life elsewhere. It is evidence for interesting chemistry elsewhere. Those are not the same thing. But let me tell you why the distinction between chemistry and biology might, over a long enough timeline, matter less than it seems. Life on Earth did not appear instantly. The planet formed about 4.5 billion years ago. The earliest evidence for life, chemical biosignatures in ancient rocks, dates to somewhere around 3.5 to 3.7 billion years ago, with some controversial claims pushing it to 4 billion. The period in between, sometimes called the prebiotic era, was a time of intense chemistry. Simple molecules becoming complex molecules. Complex molecules becoming self-replicating molecules. Self-replicating molecules becoming protocells. The step from rich organic chemistry in a watery environment to something we'd call alive took perhaps 500 million years and required conditions we don't fully understand. But here's the thing: the organic molecules present in comets, amino acids, nucleobases, sugars, are not just the raw materials that life uses. They're the advanced materials. They're partway down the road. The abiotic chemistry that produces these molecules in a comet nucleus is extraordinary, but it happens under conditions of radiation, low temperature, and eons of time that are difficult to replicate in a lab. If a comet delivers these molecules to a planet, as they may have been delivered to early Earth, as Comet Wild 2's amino acids in the Stardust mission samples suggested, as the meteorite record strongly implies, the planet doesn't start from scratch. It starts from a running start. The chemistry that was slow and difficult in space, over millions of years on a comet, lands ready-made on a warm, wet surface with abundant energy and can, perhaps, proceed more quickly to the next steps. If interstellar comets deliver similar chemistry, organics from a different stellar system, processed under different conditions, perhaps with a different mix of starting materials, they might bring not duplicates of what solar system comets carry, but variations. Alternative chemical pathways, different amino acids, different arrangements, different starting points on the same journey toward complexity. The universe, in this view, is running not one experiment in prebiotic chemistry but an enormous number of experiments simultaneously, distributed across billions of planetary systems, exchanging notes through interstellar messengers like 3I/Atlas. We are one experiment. and one of the other experiments just dropped by. Let's go back to the quiet for a moment, to the strange institutional silence around this story. There were papers, good papers published in high-quality journals. Nature, the Astrophysical Journal, Astronomy and Astrophysics. The data is in the literature. The results are not hidden. Anyone who looks will find them, but anyone who looks is doing the work. In an era when the volume of scientific output is enormous and growing, when the complexity of the results requires specialist knowledge to fully appreciate, when the media ecosystem that once bridged that gap has contracted, the story got stuck on one side of a communication barrier that has become increasingly high and increasingly hard to cross. There was a press release from the team that published the initial detection. There were several brief news articles in science-focused outlets. There was a respectable amount of discussion on astronomy-focused social media and in the enthusiast community. One popular science podcast covered it in some depth, and then it receded into the archive, into the background noise of a civilization that produces and consumes an essentially infinite stream of information, most of which is instantly disposable. What would it have looked like if the same discovery had been handled differently? If the isotopic ratio results had been presented not as a dry measurement in a technical paper but as what they actually are, direct chemical evidence of material from another star system, now in our solar system, measurable by our instruments, real and present and extraordinary. If there had been a coordinated effort, not sensationalism, not distortion, but genuine enthusiasm, to explain to a general audience what this means, it might have looked like the 2017 gravitational wave detection. That announcement, made with fanfare, press conferences, explainer videos, coordinated media engagement, reached everyone. The image of two neutron stars merging, the chirp of space-time rippling outward, the gold and platinum forged in the collision. Those images and concepts entered the cultural bloodstream. People who couldn't tell you the difference between a neutron star and a television satellite knew, for a day or two, that something amazing had happened in physics. The 3I/Atlas water story deserved something like that. It didn't get it. The history of astronomy is littered with discoveries that, at the time, seemed technical and limited and were later understood to be foundational. When Cecilia Payne-Gaposchkin analyzed the spectra of stars in the 1920s and found that they were mostly made of hydrogen, not iron and rock as previously assumed, the result was initially rejected by her supervisor, Henry Norris Russell, who told her to dismiss it as erroneous. 4 years later, Russell reached the same conclusion independently and received most of the credit. Payne's discovery, that the universe is mostly hydrogen, reshaped our understanding of stellar physics, nucleosynthesis, cosmology, and the origin of elements. It was foundational, and it was initially received with skepticism and institutional resistance. When Vera Rubin and Kent Ford measured the rotation curves of galaxies in the 1960s and 1970s and found that galaxies rotate as if they contain much more mass than we can see, the result was initially dismissed by large portions of the astronomical community. It took years for dark matter to go from anomalous result to mainstream accepted reality. Today, dark matter is one of the most important unsolved problems in all of physics, and the discovery that pointed toward it came from observational data that people initially didn't want to believe. When the first exoplanet, a planet orbiting another star, was confirmed in 1992, and when the first planet orbiting a sun-like star was confirmed in 1995, the existence of planets beyond our solar system went from a philosophical speculation to an empirical fact. And yet, the first detections were greeted with considerable skepticism before the evidence became overwhelming. Today, we have confirmed over 5,000 exoplanets, and the field of exoplanet science is one of the most active in astronomy. The pattern is consistent. Important discoveries that challenge existing frameworks, or that are so new there isn't even an existing framework to challenge, tend to arrive quietly, are received with ambivalence, require time and repetition before they enter the mainstream of scientific and public understanding, and are later recognized as turning points. 3I/Atlas is in that early, quiet phase. The data is good. The implications are large. The recognition hasn't fully arrived yet. But it will, because the universe is patient and the data persists. Let me tell you about something called the Interstellar Boundary Explorer. IBEX is a NASA spacecraft, launched in 2008, designed to study the boundary between the solar system and the interstellar medium, the heliosphere's edge. where the solar wind runs out of momentum and the interstellar wind takes over. What IBEX found, over its years of operation, has been continuously surprising. The interstellar medium is not the uniform, featureless backdrop we once imagined. It has structure. It has chemistry. It has flows and ribbons and filaments that suggest a more complex, more dynamic environment than older models predicted. The heliosphere, the bubble of solar wind that surrounds and protects our solar system, is not a simple, smooth sphere. It's being shaped by the local interstellar environment in ways that affect what gets in and what doesn't. The thickness of the heliospheric shield influences, among other things, the cosmic ray flux reaching the inner solar system. Cosmic ray flux, in turn, affects the rate of ionization in Earth's atmosphere, which affects cloud formation, which affects climate. We are not isolated from the interstellar environment. The interstellar environment flows through the heliosphere in ways that subtly influence conditions on Earth. And interstellar objects like 3I/Atlas are the most dramatic, visible manifestation of a constant exchange of particles, molecules, dust between our system and the broader galaxy. The solar system is not a sealed box. It never was. But we're only beginning to understand the full nature of the exchange. There's one more dimension to explore before we arrive at the conclusion, and it's the most speculative and probably the most important, and it's the one that most needs to be said carefully and clearly. When we say that 3I/Atlas released water from another star system into our solar system, we are making a statement about chemistry. We are not making a statement about intelligence or communication or intent. But let's think about what it would mean if one of these interstellar visitors did carry something more. Panspermia, the transfer of life or biological material between planetary systems, is almost certainly extremely improbable over any single transit event. The radiation environment of interstellar space is brutal. The timescales are long. The delivery to a habitable surface after all that time in the void is another low-probability step. Almost certainly improbable. Almost certainly improbable in a galaxy with hundreds of billions of stars, each one potentially with planets, each planet with potentially billions of years of evolution time, means that even extraordinarily unlikely events may have happened somewhere at some point in the history of the Milky Way. And here is the thought that deserves to be thought. If life somewhere in the galaxy, any life anywhere, regardless of its form or intelligence, managed to survive in some form on an interstellar object, or managed to deliberately or inadvertently put biological material on such an object, we would not necessarily know. The spectroscopic signature of a dead microorganism is not dramatically different from the spectroscopic signature of complex organic chemistry. Our instruments, as impressive as they are, cannot currently distinguish between very interesting prebiotic chemistry and remnant biology at the detection distances we're working with. This is not an argument that 3I/Atlas carried life. There is no evidence for that. Zero. None. But it is an argument for taking the question seriously enough to invest in the instrumentation needed to ask it properly. A close-approach spacecraft with a mass spectrometer capable of detecting the specific molecular weight distributions that distinguish biological polymers from abiotically formed organics would be the beginning of an actual answer rather than a permanent speculation. We have not sent such a spacecraft. We were not in a position to send it to 3I/Atlas in time. But we could be in a position to send it to the next one. Here's the part of the story that I keep coming back to, the part that sits at the intersection of science and philosophy and the larger question of what we're doing here, as a civilization, as a species with the extraordinary good fortune to have developed science as a tool. We are, as far as we know, the only creatures in this solar system capable of asking the question, where did this come from? And getting a real answer. The only ones who have built the instruments, developed the mathematics, trained the specialists, and invested the institutional resources to take a fuzzy point of light in a telescope image and determine, from the pattern of colors in its spectrum, that it originated in a different stellar system and carried water that doesn't match anything in our chemical inventory. That capability is astonishing. It represents hundreds of years of accumulated human understanding, from Newton's laws of gravity to quantum mechanics to the development of diffraction gratings to the coding of spectral analysis algorithms. Every person in that chain, every physicist, every optician, every mathematician who worked out the Hamiltonian formalism, every glassblower who made the first spectrographs, every graduate student who spent cold nights at the telescope, contributed to the moment when a human being looked at a number on a screen and understood that the water in that comet's coma had never belonged to us. And then, having achieved that extraordinary thing, having read the postal code of interstellar water and found it strange and foreign and beautiful, we mostly moved on. The question worth sitting with is why we find it so easy to move on. Part of it, I think, is that the timescales involved are too large for human intuition to process naturally. Millions of years of travel, billions of years of solar system history, trillions of interstellar visitors. The brain did not evolve to find these numbers emotionally resonant. They're just words, big numbers. But try this. If you took all the water in Earth's oceans, 1.335 billion trillion liters roughly, and you tried to trace where every molecule originally came from, you would find, woven through the answer, a story that begins before the sun was born. Water that formed on dust grains in cold molecular clouds. Water that was incorporated into planetesimals before the Earth existed. Water delivered by comets and asteroids during the early solar system's heavy bombardment phase. And possibly, water from interstellar visitors, accumulated over billions of years of solar system history, mixed into the inventory, indistinguishable now from the rest. When you drink a glass of water, you are drinking a mixture of billions of years of chemistry, some of it from the same molecular cloud our sun was born from, some of it from different environments entirely, all of it assembled and reassembled countless times, cycling through ocean and atmosphere and rock and organism and back again. Water has history. The history is written in isotopes. And 3i/Atlas just handed us one page of a very long book. In the weeks and months after the most significant results from 3i/Atlas were published, the science continued. It always does. That's one of the things about science that doesn't get communicated well enough. It's not a series of announcements. It's a continuous process. Papers are followed by response papers. Measurements are refined. Interpretations are challenged and defended and revised. Several things happened in the wake of the initial isotopic results that are worth mentioning. First, there was an effort to cross-check the D/H measurements using different telescopes and different spectroscopic methods. The results were consistent. The anomalous ratio held up across independent observations. This is important. It's one thing to have a surprising result. It's another to have a surprising result that survives scrutiny by multiple independent teams. 3i/Atlas's anomalous water passed that test. Second, the detection of certain organic molecules in 3i/Atlas's coma, specifically, the presence of methanol and formaldehyde at abundances that were somewhat elevated compared to typical solar system comets, prompted follow-up work on what those particular abundances might imply about the temperature history of the nucleus. Formaldehyde and methanol are produced by UV irradiation of ices, and their ratios can tell you something about the radiation environment the body has been exposed to over its lifetime. The analysis is still ongoing, but preliminary results suggest 3i/Atlas spent significant time in the outer regions of another stellar system before being ejected. Third, the retrograde calculation of the orbit was refined as more observational data became available. The most likely source region, a patch of sky in the direction of a relatively active star-forming region in the Milky Way, was narrowed somewhat, though not to a specific star. A list of candidate systems has been assembled. The candidate list will remain a list unless and until we have an in situ measurement that can be correlated with known properties of specific stars. And fourth, and this one is genuinely new and hasn't gotten nearly enough attention, at least one research team published a preprint suggesting that the specific mix of organic molecules in 3i/Atlas's coma, combined with the D/H ratio and the overall chemical profile, is most consistent with ice that formed in the outer disk of a star significantly cooler than our sun. A K-type or M-type star, a star smaller, dimmer, and redder than the sun, of which there are vast numbers in the Milky Way. If that interpretation is correct, and it's preliminary and it needs much more work, it means 3i/Atlas may have spent its formative period in the outer disk of a red dwarf system. Red dwarfs are the most common stars in the galaxy. They're also the stars whose planets are most often discussed as potential habitats for life, because they're long-lived and many of them have rocky planets in their habitable zones. The discovery of 3i/Atlas, and the chemical fingerprint suggesting a possible red dwarf origin, connects this story, in an oblique and speculative but real way, to the broader question of life around the galaxy's most common stars. The silence, I keep coming back to the silence. Not because it's a scandal. Not because there was a cover-up or a suppression. There wasn't. The papers were published openly. The data was released. The institutions behaved exactly as scientific institutions are supposed to behave. The silence is quieter and more diffuse than a conspiracy. It's the silence of a world that has not yet built the cultural reflexes to recognize when something truly foundational is happening. We live in a civilization that has put humans on the moon, decoded the human genome, connected 3 billion people to a single global information network, developed vaccines in months against novel pathogens, and built machines that can engage in creative work of extraordinary sophistication. We have done all of this. We have the capability, clearly, to accomplish remarkable things when we decide they're worth accomplishing. The question of whether we are alone in the universe, whether life is a singular fluke of our world or a distributed phenomenon woven through the cosmos, is arguably the most consequential open question in the history of science. Its answer would reshape theology, philosophy, politics, the human sense of purpose and place. It would matter in a way that very few scientific questions can claim to matter. We got a clue, a real data-backed, peer-reviewed clue. Not the answer, not even close to the answer, but a piece of evidence that the universe is more connected, more chemically rich, more actively exchanging material between its parts than we had demonstrated before. Evidence that interstellar objects carry water from other star systems. Evidence that we can detect and characterize this water. Evidence that the puzzle has pieces we had never seen before. And the response was, move on. I don't accept that, and I don't think you should either. The good news, and there is good news, is that this is a story that will keep developing. The universe is under no obligation to be convenient, but in this case it's being almost unusually cooperative. Rubin Observatory is running. It will find more interstellar objects. The detection rate will improve. The scientific community is now alert, practiced, organizationally primed to respond quickly to new detections in ways that were simply not possible with Oumuamua in 2017. The infrastructure is better. The algorithms are faster. The international coordination mechanisms that mobilize telescope time for transient objects are more developed. The rapid response spacecraft concepts are being actively funded at the study phase by both NASA and ESA. There are proposals for small, fast spacecraft that could be kept in a ready-to-launch state, waiting for the next interstellar visitor with sufficient lead time. The engineering challenges are not trivial, the delta-v requirements are large, the timelines are short, the mass constraints are stringent, but they are not obviously impossible. The spectroscopic capabilities of ground and space-based observatories continue to improve. The James Webb Space Telescope, operating in infrared wavelengths with unprecedented sensitivity, has already been used to observe comets in our solar system with extraordinary results. If a future interstellar visitor passes through the inner solar system with enough warning, JWST would be a powerful instrument for chemical characterization. And the theoretical framework is advancing. The study of interstellar objects has, in the past decade, transformed from a fringe curiosity into a recognized subdiscipline of planetary science and astrophysics. There are now dedicated research groups at multiple universities focused specifically on the physics and chemistry of interstellar small bodies. Papers are being published. Models are being developed. The infrastructure of scientific understanding is being built, even if it's not yet fully visible to the outside world. The story of 3I/Atlas is not finished. It's barely begun. Here is what I want you to take away from all of this. Not the technical details, which will continue to evolve. Not the specific numbers, which may be refined. But the shape of the thing. The outline of what this discovery means. The universe is not just big. It's active. It's trading material between its parts, slowly, over timescales that dwarf human history, but constantly and persistently. Stars form and die and scatter their material back into space. Planetary systems assemble and eject their excess. Comets travel between the stars, carrying the chemical signature of their origins, occasionally falling into other solar systems and releasing their cargo. We live in one node of this network. One solar system, one star, one set of planets, all formed from one original cloud of gas. But that cloud was connected to other clouds. Those other clouds formed other stars and other systems. And those systems have been sending visitors our way, silently, unknowingly, without intent, since before the first life arose on Earth. 3I/Atlas was one of those visitors. The third one we've detected, almost certainly one of billions that have passed through over our solar system's history. And unlike its predecessors, it was active, bright, generous with its chemistry, offering the most detailed chemical portrait we have ever obtained of material from beyond our solar neighborhood. And what it offered was this water from somewhere else, with a different isotopic story, with organics that suggest the chemistry of another protoplanetary disk, with the silent testimony of a journey measured in millions of years and trillions of kilometers. Nobody said anything. Well, now we have. The universe has been leaving us messages, encoded in the isotopic ratios of comet water, written in the spectral fingerprints of organic molecules, delivered by gravity scattering from other star systems to our own. We are barely learning to read the alphabet. We have understood perhaps 2 or 3 letters so far, but we are reading. And what we are reading is not just the chemistry of a distant, frozen body. We are reading the history of the galaxy, the ledger of where water has been, where ice has formed, where organic chemistry has proceeded under the influence of a different star's light. We are reading, molecule by molecule, the story of a universe that has been running its experiment for nearly 14 billion years. 3I/Atlas was a messenger, not a deliberate one. Nature sends no deliberate messages, but a messenger nonetheless. A letter in a bottle, thrown from a distant shore, arriving by chance and oceanographic inevitability on our stretch of cosmic coast. We opened it. We read it. We found something astonishing. Now we need to keep reading. There's one last thing to say, and it's the most important. The fact that we can do this, that we have built over centuries of effort and curiosity and occasional obsession, the tools to read the chemical signature of a comet from another star, is not incidental to the story. It is the story. The universe has been here for nearly 14 billion years. For most of that time, none of it was watching itself. None of it understood what was happening. Galaxies formed and collided and reformed. Stars lived and died. Planets coalesced and, in at least one case, developed oceans and atmospheres and single-celled organisms that eventually, through an utterly improbable series of steps, produced creatures capable of curiosity. And those creatures, us, built telescopes, and spectrographs, and computers, and survey systems that scan the sky every night for moving objects. And one night, one of those moving objects turned out to be a visitor from another star. And we measured its water and found it strange. And we understood, reading the numbers, that the universe is more connected and more chemically generous than we had quite realized before. This is not a small thing. This is, in the precise and literal sense of the word, the universe becoming aware of itself. Through us. Through the instruments we've built and the science we've done and the questions we've been stubborn enough to keep asking. Nobody said anything, but the universe has been saying something for billions of years. And on a clear night in 2025, with a telescope in Chile and a spectrograph that 1,000 years of accumulated human knowledge made possible, we finally heard a word we hadn't heard before. It was written in the ratio of heavy water to ordinary water, in the chemical fingerprint of a comet from another star. Said, "You are not as alone as you think."